bummer. And I'm an engineering manager at Square. I've been a imposter in the Ruby community for about 10 years now. Honest to goodness, I really feel like I don't know what I'm doing. I'm really good at it now. I just don't feel like I know what I'm doing. So imposter syndrome, it'll kick you. And what I'm talking to you about today is something that
do you have slides or a screen share running or something?
Yeah, I'm about to. I'll
Okay.
open it up now, actually. I want to talk about, well, first of all, I'm going to pick my terminal. Good idea. Get that set up. When I joined my current company, Square, I was pretty good at writing source code, but I wasn't so good at knowing what happened after I was done with it. So, okay, hold on, fighting software here. I had to learn, like, what do you do after you're done writing the source code? Like, what happens when you like throw it over the wall? Like when you give it to Heroku or something, or when you put it in AWS, what actually happens to it? And then how do you debug it there? Because I know how to debug the source code maybe to figure out like, okay, why is this, why do these types not line up? Or like, why do my tests not pass? But what do you do when you need to debug like the website is slow and it's on beefy hardware, or the database says it's out of, like, has too many connections? Like, how do you get too many database connections? And what do you do to remedy that? And we'll go through some examples. Awesome, there we go. I'm gonna start sharing my full screen. And you're gonna see my click meeting, which is inappropriate. So I'm gonna minimize all this. And here we are. All right. So we have some Ruby code. We've deployed it to production and it's out there. And then we get some reports that it's slow, or the database ends, or it can't connect Redis, or like Mongo is up but unreached, and everybody else can connect to it, but our app can't. Like, how do you debug this? How do you begin to debug this? To talk about this, first I just want to talk about the difference between the kinds of dependencies in development when you're just writing the code versus when it's out there. So in development mode, when you're writing source code, your dependencies are Ruby gems and other source code files and objects. You know, you depend on a logger, you depend on another class or something. But once you're done with the theoretical part, the text file, and you deploy it, your dependencies are every transistor on the hardware you're running on, and between you and other services you're trying to connect to. So it's a lot of things, and it's all the CPU, it's the memory, and it's the hard drive. But more specifically, it's probably something like kernel resources. Usually they're issued as file descriptors, which we'll cover in a second. So what you need to figure out is which of these dependencies are not working, or not working for me in the way I expected. And to do that, you have to figure out what are my dependencies? Like, what is this running process? What does it depend on? So we're going to create a running process. And oh yeah, in the particular distro Linux I'm using, IRB isn't a thing, but IRB 2.0 is a thing. And I've now got a running Ruby process. This is the simplest possible thing. We're going to inspect the barest Ruby process first and just see what it has, because a giant Rails app is going to have like so many more dependencies. We'll just blow up the screen. It'll be hard to see. So to begin with, I'm just going to say process.pid. Now this is where everything starts. My notes are down here on my phone, so if I look down, that's fine. You're going to run into probably 3 kinds of problems. One is the app starts to behave slowly. One is that it's using much CPU, like it's just burning CPU, or it's using too much memory. And a third one is that it's just not, you're getting an error of some kind, like a resource is unavailable or something that can't connect. And the 3 causes for that are that either you have an application bug, like every time you run something, you register a new handler, and so the handlers that get executed each time grow over time, and so like each request you're doing more and more things until the thing grinds to a halt. That kind of bug is pretty nasty. Or you have resource exhaustion of some kind. You've run out of CPU, you've run out of memory, you've run out of file descriptors, you've run out of hard drive space, something like that. You run out of network bandwidth. That can happen. And the third, and this is the trickiest one, is a misbehaving or slow resource. You can write to the hard drive. It just takes 40 seconds every time you try to write. Really? I've seen this recently, actually. So this is real. You can find yourself in a situation where everything's working fine, but it's working at like 1991 speed, and you got to figure out what is actually going on and what is causing trouble. And I'm just going to tab chat because I realized I don't know if you guys are going to interrupt me with questions. So if you are, I'll have to check periodically. Okay, we've got a running process. Let's take a look at it. The things you can do with this, primarily the first thing you should look at is the htop or top. I just want to see, what am I running? I'm going to full screen this and down. All right, down far away, I would find the IRB command. But what is important is up here on top, is there anything burning the CPU at like 100% that is a program I recognize? There's nothing there, so I'm going to ignore that. I don't think this idle IRB process is the thing that's causing us problems. All right, well, what else is going on? How can I look at this? The next step would be a command called strace. Strace has been around since like 98, 99, and it's on every Linux distribution, and I think BSD. Yeah, definitely, but not on OS 10. So you've got something called dtrust or dtrace on your Mac, but on a Linux machine, and all my examples, by the way, are going to be on Linux machines just for helpfulness of one specific kind of environment. I'm going to say, okay, I've got this process ID. I'm going to strace it. Strace p process ID. All right, it's got some output. Process 63994 attached, interrupt to quit. Read 0. What does that mean? Well, if I go over to my IRB session and I tap a key, like J, here's what happened. It read from 0 a J. It wrote to 1 a J, and then it did some whatever RT sig proc mask read whatever. This is standard input. 1 means standard output, and the J was typed from me into standard input, and it was written back out to me. It echoed out, not like I was typing a password where it's just hidden. And I can see these system calls happening in real time. And this would be a good time to stop and explain a system call. Now, a lot of folks who are watching this probably know way more than me about this, but I know that some people who are watching this video are going to be brand new to things like the kernel and system calls. So let me just go over that. There are only 2 things that a process can do on your machine. It can do what's basically pure math. It can, just compare numbers and move bits around in memory and create objects and come up with a result, sort of like what you think of as programming. Or it can make system calls. System calls are how a program interacts with the outside world. It's basically just a way of the program saying, kernel, Linux, Windows, whatever it is, I want you to do something for me with your like privileged view of the world. And when you're done, please get back to me in this fashion. And what I want you to do is either I want you to read to something or write to something, or set a setting somewhere, or there's actually a whole bunch of system calls you can make, and you can watch them happen with strace. So we saw read and write, and we saw it with watching it over strace. Now sometimes strace is not even going to come up. You're going to run this, and your process is so borked that nothing will show up. Maybe the whole machine is slow. You can get way more access about your computer, about your process, by just looking in the proc file system. Now, that is going to be mounted downnet/proc. It has a bunch of stuff. It is not on your hard drive. This does not exist. This is not a thing that's taking up disk space. This is something that the kernel, which shows you your hard drive on a path, also just sort of adds in there. It mounts this like proc file system that shows you process information. So I've got my process ID up there, 63944. All right, I'm going to cat proc 63944. That's it, it's just an integer. Syscall. No. What is that? 63, oh, I typoed it. 994, syscall. And full screen that just so you can see it all in one line. This is absolute gibberish. This is really unhelpful, right? Well, except that the far left thing, that 0, is a number that maps to the system call you wish. that is currently being executed. So this is the current thing your process is doing. And you can look up in your header file on your machine what that maps to. Now, we actually can see it right here. It happens to be the read system call. You can see strace doing that. So if you saw a number other than that, you could look it up and be like, okay, my process is wedged. I don't know what it's doing. I see there's like a 48 there. No idea what that means. I'm gonna look it up in an index somewhere in a man page. And you'd be like, oh, 48 means wait for video driver or something. And then you can get back to your colleagues and say, this appears to be looking for a video driver. I don't know what's going on, but here's why the process is messed up. And you will appear to be a genius, and all you did was you catted a file, proc, process ID, syscall. All right, there's some other things you can look for in proc to tell you about this particular program. I'm going to cat, actually, first I'll list. And if you have a Linux machine, please follow along at home. Proc C994. What are the things I can do? I can look at network information. I can look at things like the current working directory. If I'm running a file that I've deleted from the hard drive, but it's still running, I can recover it because it's in this exe right here. Yeah, it's a symlink to user ruby to bin ruby. That's what's actually running. Now, if I delete, I won't, user ruby20 bin ruby from the hard drive, because the way the kernel works, it's going to have that file cached in memory. And you'd never be able to access it by just trying to look for it, but you could just read this file out of proc, and you could recover it. Very handy if you fat finger some sort of RMRF. Other things I can do are I can cat proc .63994 stack. Now this is pretty handy because this is something that strace can't show us. I'm going to temporarily pause this strace because it's about to be really loud. Now the stack is the backtrace for your C program. And I should mention, for this talk, I'm only talking about MRI, and I'm only talking about Linux. If you're using JRuby, you're actually using the JVM, which is a whole other beast, and there's fantastic debugging tools for that. The JVM has some really good standards. If you're using Rubinius, it's also a whole other beast. It is a C program. I mean, even the JVM is a C program. So you can use this stuff for Rubinius, but it's going to look a little bit different, and it has other tools for introspecting it. Now, most of us are going to encounter Matt's Ruby implementation, MRI, Ruby 2, whatever now. And so it's going to be a pretty standard C program that you can debug like any other C program. And right now I'm looking at the stack. NTTY red. Oh, great. Thanks, Facebook. So, NTTY read. It is blocking on a read call. If I tell it to do something else, like I'm going to select on, actually, no, I'm going to sleep. I'm going to sleep 20. I'm going to cat the stack again. Now the stack has changed entirely. If I have a process, I want to know, what are you doing right now? And how did you get there? Like in C terms. I don't know maybe what the function do futex is, or futex wait, or futex wait QME. I have no idea what that last one means. But I do know that it changed. I do know that it was NTTY read, TTY meaning your terminal. And then it turned into like wait Q. So if you've got something totally borked, you can just cat what's the current stack and take a look at it. Now, additionally, there are in proc 6399 various tasks. These are the threads that are involved. This particular IRB session apparently has 2 threads right now, and I can get a stack for each of them. So while it's sleeping, I'm going to cat them both out. Now, one of them starts here. That's the thing we saw a second ago, the primary threads stack. And the other is here. So it looks like there's a sleep. And while it's sleeping, there are 2 threads. One appears to be doing some sort of polling, scheduling, timeout. Doesn't matter what that function is. You can tell what the name of it is, kind of what it does. And the other is waiting. And now that sleep is returned, it's doing scheduled timeout and TTY read. All right, so that's pretty low level, but it proves pretty handy in a pinch. And great. Now I want to look at what other dependencies this is using. So one dependency is like the kernel. It's making calls to the kernel. Another is any file that it needs on disk. Now, when you boot basically any program, with very few exceptions, it's going to not be in itself. It's not going to have all of the code it needs and all the functions it needs to like behave as a citizen on your Linux machine. What it needs is some other helpers. It'll have in it like the core programming functionality it's supposed to do, but it will look on the hard drive for things like how do I read and write to the screen? How do I make network calls? How do I do cryptography? How do I do access to the database? Especially if, like, let's say you have a Ruby app and it's connected to MySQL, you may have at some point run into some trouble installing the MySQL gem because it'll say like extensions couldn't be compiled, or some sort of like GCC not found or something. It's trying to do something tricky, and what it's doing is it's creating a separate file from Ruby executable on your hard drive that Ruby can use to connect to MySQL. And we can take a look at that. Now, the way you look at the open files that a program is using, really all the dependencies on the file system is just list open files, or LSOF. I'm starting to memorize this class ID. I'm going to full screen this. And let's walk through the kinds of dependencies it has here. Now, the first couple are the paths that it needs. I want to check chat. Okay. Nobody's telling me like my video is out or anything, so I'll keep going. So the first couple are just like directories that are open, that the program has been executed in. Home Jack Danger is where I started this program, and it is using that as a resource that it needs from the kernel. Now these other ones are a bit more interesting. There are really two kinds here. There are files, all these here, that are all on the hard drive. And you'll notice they all have a .so in them. Now, .so stands for shared object. Shared object is just a C program that doesn't execute. There's like a header in the file that tells you whether if it's like a 2, it's a shared object, it's a 3 at a certain byte location, then it's executable, or vice versa. And we use these, like the program runs and is linked to use these specific files to do things it needs. Take a look at a couple of them. It's going to use this for crypto. If there is an issue with like a giant vulnerability with the way cryptography works in the CentOS or Red Hat distribution, what will probably happen is you have to install an RPM, which compiles some C code when it installs, and it puts a new shared object on your machine. And your Ruby will be patched when it picks up a new version of this. It would be, libcrypt 2.13.so or something. And if your Ruby process is running while you install that, just like how you can retrieve the exe file from a hard drive that it's been deleted from because the Linux kernel caches it, until you restart your Ruby program, you will not have the new version because it's linked against this old one. And when you've restarted it, I recommend you take a look at open files to see which one you're actually using, because it's not at all uncommon that you'll have like maybe 4 or 5 different versions of the MySQL gem installed somewhere, each with their own compiled shared object. And you'll have to figure out a way to identify which one you're using and which one you need, and make sure that you're like linked against the right one. And this connections, which one to look up, happens at what they call linking time. It's like just after or during really compiling time, where you take C code, you put it up in an executable thing, but then you like connect it to the stuff on the hard drive it's going to need, or tell it roughly where to look once it boots. All right, and to look a little bit closer at this, let's see end curses. Now this is something that prints stuff to the screen. This like helps you manage your TTY management, or PTY. Actually, my understanding of terminals is pretty poor. So it's something about drawing stuff on the screen. All the stuff I'm doing here with like tmux, you may have noticed I've got this Yellow numbers in the top right. It's all tmux, very fun. And that's, I believe, all curses. So I'm going to take a look at that. The format for this file is going to be probably an ELF format, executable Linux file, something like that, whatever. And with read elf.h, I can take a look at what this is. And you'll notice right here, it says it is a shared object file. I just read this file. I ask, what kind of stuff is it? What is this like on my machine? If I did the same thing with the Ruby file, it would say, oh, this is executable. They're basically identical in that they have functions in them and some sections of like function code, some little startup boot section, and it has read-only data. And then programs are pretty standardly laid out in this format. But there's one bit somewhere right near the top, the first few bytes, that says, is this a shared object that you can like use, or is this something that runs directly? And I've never tried to flip that bit and run a shared object, but I'm sure it wouldn't work. Actually, I'm not sure at all. Whatever. Please try that. Okay, these are the kinds of resources we're working with. I'm going to go back to our IRB example. And I want to talk about file descriptors a little bit more specifically. If you are in a data center, not like in it, but like SSH to it, and you have some process that's misbehaving, or especially if it's running out of the file handles, open files, or if it's having trouble connecting to something, the problem is at some point going to require you to look at the file descriptors that this program uses. I'm just going to chat again. Oh, question. So total memory occupied by the process also includes its own copies of the system libraries and objects loaded by it. I don't think so. I don't know. There's something about virtual memory and shared memory in there that may not include that, that total. Oh, great. And Chuck is telling me if there's a problem, I'll unmute you and stop you. Great. Full speed ahead, everybody. And I do not know whether the memory total involves a shared object, but I suspect not. Or maybe only after they're used. I don't know. That's a great thing to look up, or really just like experiment with, because you could watch it as you like look at the file sizes of each of those files. There's LSOF, and keep track of file sizes, and then look at how much memory you're using of different kinds, and then exercise the functions inside that in your IRB session by like actually using the OpenSSL library somehow. So I just ran that, and take a look at LSOF. This now has, guess what just showed up? I just required OpenSSL, and it required this shared object. This is not a .rb file that was required, or I mean, there probably was at one point, but it picked up these OpenSSL.so files, and actually a whole bunch of these too, that are now going to be used. So I've just increased my memory footprint by requiring a file. But I don't know if it's right then or when I start using it. Somebody please do investigate. All right, I'm going to actually start over with a couple of these screens just to make the next example a little bit clearer. This is an IRB session. It's brand new. It has it has 7507 7 files, but just the basic ones. You'll notice a second ago it was more than a full page. And I am going to now talk about these things down at the bottom. The files are like shared objects that are used by the program. These, you'll notice under the fourth column, the FD column, under the FD stands for file descriptor. There's current working directory, root directory, RTD, sure. Then a bunch of stuff in memory. And then these are an integer followed by a letter. These are file descriptors. 0, 1, and 2, you're going to see just friggin' everywhere. 0, 1, and 2 are standard input, standard output, and standard error. If you've ever done, echo thing, and you pipe it to a file, but then you think, oh, you know what? Actually, I'm gonna pipe. Let's see. pipe it to the first file descriptor. Or if you've ever seen this redirect stuff, all you're doing is you're saying, oops, I've got these file descriptors, and I want you to pipe 2 to 1, or 1 to 2, or 1 and 2 together and into a file. And you can create as many file descriptors as you want. You can even have different file descriptor numbers for your standard in, standard out, and standard error. It's uncommon, but it's just a program, and you can kind of do what you want. These are computers. It's hard, but once you learn it, it's easy. And then these others, these pipes, they're something to do with the streaming involved in JRuby. I have no idea. So what we're going to do is we're going to create new file descriptors. I'm going to say f equals file.new file. Right. I've just created a new file. It's a file object. Look at that. I haven't written to it, but now it's right here. And the file descriptor is 7. Now that was issued by the kernel. A file descriptor is how your program knows which resource is which. And they're not some rich object, they're literally just an integer. And you can only have as many as the number of integers your system can have. It's pretty simple. If you saw Steve Klabnik give a talk yesterday, which I highly recommend, we talked about Rust and system programming, he made a comment that I cannot agree with more, which is that low-level programming is easier than web programming. If you are a web programmer in a browser today, you have to be brilliant. If you're doing the kind of stuff I'm doing now, you just have to read some documentation and sit next to somebody who knows what they're doing for a little bit, or play around, or watch this talk, or ask me questions on Twitter or something, and then suddenly you're really good at this. And it doesn't change, because this stuff's been around since the 80s. So learn it once, and then there'll never be an Angular 2, for this. This is here to stay. So way easier. And your resource, just an integer, 7, in write mode. Now, I want to create another one. Sure. The fact that it's the same file name doesn't really matter. We got an 8. That's great. Does anybody else see a problem with this approach? Yeah, a lot of files. A lot of files. Now, you can probably imagine how you get to resource exhaustion with files. I'm going to say 15,000 times using my favorite underscore notation. Map this. Too many open files. We just hit it. We just hit our limit for what the system can handle. And if I list them, yeah, it went right up to a highly suspicious number, right? 1,023, starting with 0. So exactly 2 to the 10th files are opened right now. And I don't even have handles to them, so I can't even close them right now. So I'm just going to exit it out. I can also, if I don't have references to them, run garbage collection. And Ruby has, while very seldom used, it has finalizer functions for objects. So when something is garbage collected and it's a file or IO object, it'll have .close called on it, and it'll just be picked up automatically, which is pretty good. Going to get my new process ID, 72017. All right, nice fresh IRB session. Let's watch those file descriptors happen in real time, because chances are, when you're like at a Rails app in the data center, you want to debug it, you want to see what's going on, you're not going to have the luxury of doing the thing it's doing for it, like in an IRB session, and then seeing the response. You have to just see there's this thing happening. Maybe it's pegged 4 cores because a lot of stuff's happening in C land, or maybe it's just a whole bunch of processes that are using sets of RAM. You don't know what, but it's doing stuff. It's serving requests. It's working. And so double check the chat. All right, cool. You guys are solving the memory question. Wonderful. Much appreciated. So it's doing something, and you want to watch it do that thing. So using this, this PID, I'm going to strace the whole thing. You've seen this before, earlier, read 0, which means read from standard input. That's what the IRB session is doing. But I'm going to close this, change my layout. All right, watch this as I just do simple things. That's not even Ruby. What am I doing? So this is a lot, right? This is a ton. How in the world do you follow this? Well, there's a couple things to look for. We'll go to the top and we'll just take a look at the kinds of things that are happening. First of all, RT sig proc mask has something to do with a signal mask, which means which signals to ignore or permit to interrupt the program at different times. It's a kernel thing, and it appears to be just noise in our S trace. We're going to ignore it. But we're doing read calls and write calls. You'll notice P, U, T, S. This is slow, right? This is achingly slow. If this were not me typing one key at a time, you'd see it all together. Like with, when Ruby decides to print to me syntax error, or a first line of a backtrace, or a second line of a backtrace, or a new line. So this is it printing a whole bunch of characters at once. That's what a write and read command usually looks like. And you can also see which file descriptor it's writing to. Writing to 1, standard out. If it's writing to 2, it would look like this. No idea why it wrote a \7 to standard out or to standard error. No idea at all. However, this is a bit noisy. We're going to change what it's showing. I had to look this up. This is not something I knew offhand, but I can set the commands that we track to just read, write, close, and open. A little bit easier. So I'm going to do the same thing. I'm going to say, what? And you just see me type each individual character, and then prints what. But we can do better. We can open. There we go. Now that's actually interesting. It opens a new file called file. I can do better than that. Let's see. How about file name.txt? Then you can actually track what's going on. So when I say file.open file name.txt, comma W for write mode, what Ruby turns that into is a request to the Linux kernel saying the open system call with a string in memory. In one of the registers of the CPU, there'll be a memory address for the string. File name.txt and some flags about how to open it. This just means write. And the important part is this thing at the end. There's an equals. That's the result of the system call. The return value, if you will, which is a file descriptor. It's an integer file descriptor. That is now the thing that we're going to be using to read and write to this file. So if you're trailing, if you're S tracing a Rails app and it says open file name.txt 8, you can expect later on, with some other stuff mixed in, there's going to be f.write contents. And where did that go? Weirdly, there wasn't a write to 8. Why is that? Gonna see where that went. Yeah, that didn't happen at all. All right, I probably got the syntax wrong. This is easier anyway. Starting from fresh, block syntax. Let's see it all at once. Whoops. Take 2. Here we go. We open file name.txt in write mode. We get a file descriptor 9 because I still have that old file open in memory. It's not closed. The kernel knows I have it. I might have forgotten about it. I might have forgotten to garbage collect it. Even if I did garbage collect it, if I didn't call close, the kernel says you still have file descriptor 8, so I'm only going to give you 9 for the next one, so you don't clobber the wrong file. And then we write to it with the contents. Then we close it immediately. That's Ruby's blocks in action. It's going to figure things out for you. At the right time, it's going to do an ensure block that closes stuff. And then we write to standard output the length of what was written, which is 8 bytes. Contents has 8 characters in it. And then the prompt. And then we're waiting for something else. Now, if we were tailing a real Rails app, you will see something like write I'll do it down here. Pretend this is strace down here. Write 173. This will be like a Redis call. You'll see, oh, 173, the file script 173 is being told, given the string to write hset, hashset, hkv or something. And this 173 will be a file descriptor that you previously opened on a TCP connection to your Redis server. So you can actually watch your Redis traffic go through, as long as it's not encrypted, which Redis doesn't use SSL, so it's not going to be, or it will be soon. So you can just read it in plain text, which is a security implication, actually, and why at Square we use a thing called S-tunnel to talk to Redis. It's basically like just an SSH tunnel for talking to Redis, so nothing ever goes over plain text. Okay, and how am I on time? 20 minutes. Okay. Okay, you're doing fine so far. I'm going to switch to the next significant thing to look for. I want to talk about Ruby's timeout a little bit. Now, the thing I'm trying to communicate today, I think I'm trying to help with, is if you're in a position, you're on call, you get a text message or PagerDuty page or something, and you have to go investigate a Ruby process, a lot of things could be happening, and it's probably going to be something that is slow or resource exhaustion of some kind. And one of the problems that's really frustrating is when something you require on is either unavailable or poorly available. Like, let's say MySQL maybe a little bit harder or easier to reason about, because like you'll have access to the server and it'll be like not running, so you know what to do there. But say you have some sort of cloud-based service that's like running Redis for you, or Mongo, or Postgres, or MySQL, or you're just on AWS and things are slow and you don't know exactly why. It might be reasonable to think, oh, I'll just add a timeout block to my call to this resource. I'll wrap it in like a 1 second maximum timeout. The way you do that is by requiring timeout, and then timeout, 1 second. Sleep for 2 seconds in the block, and no, it bailed on you, which is great. It's fantastic. It means that if during a Rails request you have to make some sort of synchronous call to a dependent service or resource of some kind, you can limit your exposure to the vulnerabilities of that service. Particularly if you are in a service-oriented architecture, this becomes a real big problem. And you need to look for things that could, if they disappear, make you disappear. If you, in a certain web request, do like a Google API lookup for geolocation and multiple database queries, in Rails app it could be hundreds, depending on like how you do stuff. And then like on the front end, you've got script tags for doing metrics or ads or something. The script tags, you may notice, are usually nice and asynchronous, but the stuff on the server, not so much. It's probably going to be, oh, I need this and this content here, so block and go make that call and wait for 30 seconds until server X gets back to me and puts it on the page or in my response, which is scary. And so you're like, oh, I'll wrap that in a timeout call, which is better than nothing sometimes. But there's some real nasty issues with timeout. Timeout is implemented, great, you can see that if I do roller disco. Right. Timeout is implemented in a pretty weird way. And I would like to just walk through how it is. So it's basically something like this. And you can look at timeout.rb in your Ruby distro on your machine or on GitHub, and you can see this happening. Thread 1 is you. This is super pseudocode. Thread 2 equals thread.new, sleep 2 seconds, and then raise error in thread 1. And then really quick, I'm going to do some stuff. And then it's totally going to raise an error in me if I don't do stuff quickly. So the idea is you are going and you start this thread off to the side that sleeps for the timeout period you want to allow. And then after it's done sleeping, it throws an error in you, and you have to get your stuff done so that you can, at the end, kill that thread before it bites you. Like that's actually how timeout is implemented. And there's a couple like carve outs for signal masks and like ignoring some exceptions and like block handlers in the actual implementation. But that's basically it. You've got this thread you spawn that races you, and then it gets you if you don't get it first, which is great some of the time. But I want to show you an example of when that does not work. And I need to pull this out of my notes now. Here's an example of code that is going to be problematic at best. So I don't want to get the last one. Okay. Timeout 1. All right, so this whole thing is going to have a 1-second timeout. In a begin ensure block, I'm going to do some stuff, but then I have an ensure. That is definitely going to fire. So my ensure absolutely, like it's a promise. Whatever I do in ensure, that's where I clean up file descriptor. That's where I close my open files. I do whatever I need to in my ensure block. First, I'm going to sleep for half a second. Then I'm going to open a file, get a new file descriptor. Then I'm going to just print that on the screen. I raise an error, and then I successfully run my ensure block, which, whether an error is raised or not, is always run. There's begin, rescue, ensure, end. So rescue only if an error runs, but ensure always. And unfortunately, my ensure takes a little bit of time. It sleeps for a full second first, and then I print the file again, and then I close it, which is not actually an unreasonable thing to imagine. In your ensure block, you clean something up, but maybe the call to clean something up like lazily instantiates something, and maybe that happens to involve an active record object, and maybe that's a database connection. Suddenly, you're going over the network, and everything's really slow. Notice file temp list printed once from right here, but never from right here. My file never closed. I could run this a bunch of times, and I'm going to get back in here. What's my process? The ID. I've got 15 minutes left. Sorry. Process.ID. I'm going to strace. Yeah, that was it. This as I run this. Notice I open it, file descriptor 11. I open it again, file descriptor 12. My ensure block isn't fully running. It's getting interrupted. In Ruby, your ensure block can be interrupted and can leak dependencies. Now, this is kind of like a garbage collection error where if you keep a reference you didn't know about to an object, you'll never quite get garbage collected, and you can have memory bloat. The same thing can happen with other resources. Garbage collection does not protect you against resources that the VM doesn't own. So it doesn't know that this thing still exists. That it may have forgotten about file. I bet it was actually already garbage collected, or will be soon. But Linux still knows about this file and thinks you own it. So your 13 is going to become a 14, and unless you up the limit of number of open files you can have, that'll hit 1023, and then you're going to see a request will just fail. All right, and this is why timeout is something I can't actually recommend, or I recommend using it when necessary, but know that anything you use inside the timeout block is a resource that may need to be wholly reinitialized. I've had problems when my team last year at Square was working with a ludicrously large Rails application on an even more ludicrously large MySQL database, and the connection to MySQL itself would get corrupted because we put our database calls in a timeout. The database was really, really fast, but the extreme outliers were sometimes slow. We didn't want a 4-second request to ever happen. So we're like, okay, we'll just make sure that queries can run pretty fast, which means during the timeout, well, the timeout error was raised right around the time that some sort of ensure block was happening, and we ended up messing up the connection itself. Like there was in C down there, way down in the shared object, there was some sort of state being modified, and we threw an error right then, and we caught it, and we just kept processing requests, but we used this now like messed up state to connect to our database. Very broken. If you're using a timeout block, make sure you can refresh any resource that you're touching inside of it and know what you're touching inside of it. Try to do them as small as possible. That's one huge piece of credit I'll give to Rubinius, is that Rubinius does a good job of keeping locks very small and not trying to like use the global VM lock or anything like the GIL. It like just has small locks on like sensible little places where you need locking and such. It's harder work, but it makes for a better program. All right, I've got a couple minutes left. Doug, I just read your chat. Yes, someone named Danger is telling you to be careful. Sorry. We're just going to see this timeout error happen in real time. Now, I'm going to cut down on the reading and writing we're tracing. So strace on the process ID of IRB just closes and opens. And I am now doing this. In a loop, I'm going to run basically the code I just showed you. Sleep for half a second, raise an error. I'm going to write to the file right after the error was raised, which means it will obviously never happen. And check out those file descriptors. They're just going. This looks like a perfectly fine Rails application for a long time until you run out of file descriptors. And while it's running, let's pretend this is the thing we have to debug. Bang $, by the way, means the last argument of the last command. So I know that my PID was the last thing I typed. I'm going to, that expanded. I can now list the open files. It's all the stuff from before. Standard input, standard output, standard error, some pipes that IRB likes, the thing I opened a while ago, and then stuff for this example. Up to file descriptor 34. Oh, 51, 52. That's getting bad. Well, proc, that PID, that. Can look at what it's doing. Yeah, there's a couple things sleeping. There's some timeouts happening. I know about those timeouts. And let's take a look at the file descriptors. Proc, PID, FD shows you the actual file descriptors that are in use. And luckily, my terminal gives you some nice color highlighting so I can see 6 as a pipe. It's quite pretty. You can see what these are pointing to. This is basically what LSOF is using when it looks up open files, so it's smarter. You can see these growing, and you can even, can you do that? Yeah, because there's no content going in there. But you can look at what's inside the file by like tracing the file descriptor. Going to cut that off. And there's one last thing I want to show you for opening it up to questions. And that is a little more about the shared objects that you're relying on. So we've looked at, I'll go back to one. I'm going to look at the CPU and memory that this tiny idle process is using. And 7, this is CPU, this is memory, if I recall. And PS, this tells you some things like what terminal it's connected to. And over here is me, that's my user ID. This is the process ID. But the CPU and memory are fine. Great. And open files, not bad. What if we want to look a little bit more at what's going on in here? Like, okay, we're using that libn curses. What's really in there? Well, we did this a bit ago. Read elf-h for header. But what if we want to see all of it? What's really in there? Well, this is going to be gibberish. I apologize. It's gibberish to me too. As I scroll down, and it's just ones and zeros and confusing things, I'll start to see some words. And here's one. NC has mouse. these are functions that are inside this shared object. So contrary to my previous belief that a compiled file on your machine is totally opaque and just like a black box, does whatever, you can actually kind of see what's available in there. If you see something in your stack, cat, proc, pid, stack, that it looks like it'll be a function call, it'll be a C function call. You can, if you look through the shared objects, track down what function call it is, where it is in the file. You can even disassemble the file using a free online disassembler and take a look at the reconstructed source code of that exact function by looking at where it is. And where it is happens to be here at position 221AD0 in hexadecimal notation, offset from the beginning of the file or the beginning of this section. Regardless, a disassembler could find that for you. And you'd be surprised how useful that is when you have a dependency that's misbehaving, or when you find that your application data gets stuck and is not erroring, but just stuck, and you need to look at what seems to be that item on the top of the stack that is taking all this time. You can look through your shared objects, and with a little bit of piping and grepping, you can turn LSOF and like what? Would this be 1, 2, 3, 4, 5, 6, 7, 8, 9? You can look at the headers of every single thing that you've, that frankly was interested, that you're using. And if you wanted to look at it all, grab MySQL through all of them, or mouse. Look at that. I just found every function that is used by every dependency of my program that has the word mouse in it. And this can be helpful. Okay, running out of time, I'm going to go to questions now. All right, I saw I froze a bit, maybe. Sorry, folks. Does anyone, I want a function called mousetrap too, I want to use it. All right, does anybody have any questions about any of this or comments? I know I did sort of a rapid tour of system programming. Maybe this is a good pairing with what Steve talked about yesterday. Hopefully it was. All this can be done much more safely in Rust or Go, much more unsafely in C, and frankly, just unreasonably dangerously in C++, if you're interested. Okay, yeah, feel free to rewatch. As I wrote out this talk, it was a big Google Doc. You can actually see it over here, and it's going to be a blog post. So I'll keep putting that together. Oh, command line goodness. I would love to teach command line goodness. That's a good idea. Oh, Anthony Bargnesi asks me, where do you start debugging if you see an issue? Wondering about your workflow. That is, it's a good question. And the first place to go is htop, because usually the problem is there's one process using up every core in the entire machine, and you need to kill -9 it or something. Like that's the most brutal way to do it. So that's what I start with. If that's not the case, or if it's unsafe to kill -9 it, I look at the current stack just to see like what's going on, and if have I played with RB trace as well? If so, what are your thoughts about having it hooked up in production so you always have a hook in? I have not played with it in production. I think it's a fun idea. I think it's probably worth it. One thing, let's see if I can sneak this in. One thing I've used in the past to debug things that it's not production grade. RB trace, I should look at it. Maybe it is secure enough. But you can say trap prof do and then no, I can't open. I can kill 8420. So what I did there is I told it when you receive the signal prof, print out everything you have, which is terrible. Just trap this Linux signal for each object, print it, and then end. And then I sent it that command, and I just printed it. I've done this in the past where when it receives a signal, it prints some subset, like prints the stats on the object space or something to a JSON file. And it timestamps it, and so they grow over time. This is great if things are failing in CI remotely, but not locally. You're like, well, how do you debug that? That can be okay. Anthony Barniese also says, with Ruby 2, you can require tracer, something like Ruby, require tracer, your script RB. That's great. I'm going to try that out. I like that. That sounds fun. Okay, it looks like I'm about out of time. The blog post will come up in a bit. I am at Jack Danger on Twitter. I would love to meet you. And if you're in town, I'd love to take you through Square because we have great food. And I can always pawn it off as a recruiting expense. Hey, there's a developer in town. I have to take them and feed them. Nobody will complain.
Very cool. Well, thank you, Jack. I'm still mopping up where my brain dribbled out of my ear. So, but excellent talk. Really good. I'm gonna have to go back and rewatch it. And yeah, I'm an old ops guy too. So anyway.